Okay, welcome back. I hope we had a lovely weekend. Today is class number 27. Project number 7 is officially assigned, so go ahead and grab a copy of it from your table. I want to point out that Project 7 is based on some basic probability calculations, and some of you have had very limited experience in your past math classes with probability. So there is a short video that you might want to watch. I think it's linked in the project itself. It's definitely linked in on our Moodle page. Yeah, there's a little link there in the project too. So check that out. It's 15 minutes. It's definitely worth watching if you're not super confident with your probability stuff. Okay, so that project will be due on the 19th. So you might write down Wednesday the 19th on that project. Today we cover, we start our first example of series, and we're going to be doing series every day for the next, I don't know, 3 weeks or something, all the way through the test. We are going to use the word series every single day. Any questions on the calendar? Okay. So before we jump in on page 11, just one quick announcement. I'm going to stare awkwardly at the back wall while I make this announcement. The last day to withdraw from any class this semester is this coming Wednesday, the 12th. If you are considering withdrawing from my class, please talk to me. I will tell you exactly what I think your chances are of passing. But this is not just a calculus thing. Any class, end of the day, Wednesday coming up. Any questions on that? Okay. All right, so here we are on page 11. In this class, we learned about series of numbers. Number one, a series is the sum of a sequence of numbers. We saw sequences last class. If we add up all the terms in a sequence of numbers, we get what we call a series. So for example, 1, a half, a third, a quarter is a sequence that is just an infinite ordered list of numbers. 1 plus a half plus a third plus a quarter plus ... forever is the corresponding series. Okay? Sequence is a list, series is a sum. Series is specifically for adding, yeah. The individual numbers are called the terms in the series. We want to define the sum of an infinite series, which is tricky because we're trying to give meaning to adding infinitely many numbers. So what does it mean to take 1 plus a half plus a third plus a quarter plus ... forever? That's what we are trying to give meaning to. So there is kind of a complicated definition here in 3. We're going to do 4 first, and then remind me if I forget to go back to 3, okay? Number 4, I drink 1 cup of coffee containing 100 milligrams of caffeine every morning. It is known that after 24 hours, about 6% of the caffeine is still in the body. Every 24 hours, your body processes all but 6% of that caffeine. What quantity is in the body right after I drink my coffee on day 7? Okay? All right, so right after we drink a cup on day 1. I call this thing S1. How much caffeine is in the system before your body has processed any of it? Before your body has processed anything from the first cup, 100. Okay, so we start with 100, and then immediately your body starts processing it. So the 6 that you guys all said is 1 day after this thing. So let's do that. S sub 2 is going to be right after we drink the cup on day number 2. Okay, so it's just 106, right? Because you got 6 left from the first day and then 100 new ones. So don't write this because we're going to need to write 106 in a very particular way. So don't write that just yet. But S3 is not as obvious because now we're trying to take 6% of what number? 106, which we probably don't know just like that. And then we add 100 to that thing, right? Okay, so I don't want to write 106 here because that sort of hides what's going on. So I'm going to write this calculation in a very particular way. Do write this thing down. What you did was take 6% of 100 that we had before, and then you added 100 from the new cup, right? That's 106. But I'm writing it in a very particular way. And for S3, we are going to take 6% of that entire thing that we just said, plus another 100, yes? And I'm going to write that. I'm not so interested in what the actual final single number is. I'm interested in the pattern that we're developing here. So we are taking 6% of this whole thing. That means that this first term, I'm going to imagine distributing 6% into both of these terms. So this first guy is a 0.06 squared times 100. That's 6% of the first thing, plus 6% of this green 100. Yes? And then plus one more cup of coffee that the body hasn't had any time to process. We see it? And that might be enough for you to start to recognize the pattern here. The next one would be 6% of all of this plus another 100. That's going to turn this into what power? That's going to be cubed. This one is going to be squared. This one is going to have a single 0.06 on it. And then finally, plus 100 for one more cup of coffee. You see it? So if I wanted to write down the final thing for S7, which is how much is in my body right after I drink that cup of coffee on the 7th day. Just have to think about the pattern here. 0.06 to the what power? 6, right? S3 had the highest power of 2. 0.06 to the 6th times 100 plus 0.06 to the 5th times 100 plus dot 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 0.06, a single power. And then finally, our cup of coffee.
6% from the original 100 milligrams is always decreasing too, because so like you're not going to always have that like 6 milligrams, but slowly put down as the power.
Mm-hmm. So this 100 right here that's being multiplied by 0.06 to the 6th, that was your very first cup of coffee. That was your day 1 cup of coffee. And it has had 6 days of 6%ing happening to it. It is in theory still there. At some point it becomes immeasurable with the tools that we have, right? But in theory never goes to 0. And then when did you drink this cup of coffee, which has a 5th on it? That was 5 full days ago, which was day number 2, right? And then finally, that was today. Okay, so that is our calculation. Turns out there is a very nifty way to type this thing onto the calculator. Like, it appears to be annoying to type this thing onto the calculator. I'm just going to type in this one annoying one here, 0.06 squared times 100 plus 0.06 times 100 plus 100. I think I've done that right. So 106.36, that's S3, okay? So that's kind of annoying if I want to type all this thing out. So here's the really clever way to type this in. Check this out. So we go 100, you guys are going to remember this, right? 106.36. That'll be something we can confirm here. Okay, so I'm just going to type 100 and then I'm going to hit enter. So far, so good. Then I'm going to say, okay, the next day I'm supposed to take that previous answer and multiply by what number? 106. And then I'm supposed to add, how much? 100. And okay, that is definitely the right thing to do to get the 106, but it is also exactly that same calculation every single day. You take the previous answer, you do 6% of it, and you add 100. The previous answer is now this 106, which is exactly what I want it to be. 106.36 was that number from the annoying calculation. Now it's just a matter of counting. That's day 1, day 2, day 3, day 4, day 5, and day 6. So that's our answer, which is what you would have gotten if you typed this whole annoying thing in. It's a really nice recursive way to type this on the calculator. Okay. All right. Taking a look at this list of numbers, always doing what? Increasing or decreasing? Always increasing. Does it appear that it's going to go to infinity? Yeah, it's definitely increasing the whole time. Do you think it's going to get to 107? I don't have a lot of confidence that it's even going to get to 107, even though it's increasing. Here, look, it increases by 6, and then by 0.36, and then by 0.0216. Right, it's only increased by 0.02 and change there. How about here? Yeah, the amount it's increasing by is decreasing, like rapidly decreasing. how much are we increasing by here? 0.0012, roughly. And then from here to here, 0.000, like 0.08. Right? It is increasing, but by like minuscule amounts. And this is only 7 days into the process. So it appears that by drinking this 1 cup of coffee every day, like we're not going to like overdose on caffeine. It's not even getting that much higher than the 100 milligrams that you chugged on the first day. And so if I hit enter a few more times, it doesn't take long for us to not appear to have any gain. That's just because I don't have enough digits on my calculator. It's still going up every time, but hardly by anything. So we'll just write this as our sort of long-term guess. 106.3829787, something like that. That can't be far from the right answer. Okay, so here's some vocabulary. Really what I'm interested in question 5 is what do you get when you add forever? What do you get when you add forever? Things that look like this: 0.06 to the 6th times 100, 0.06 to the 5th times 100, 0.06 to the 4th times 100, and then if you keep going forever, I want to know what you get. And it appears that we are converging, I like the word Nick uses there, to a single finite number. We are honing in, getting closer and closer and closer to some particular number, not infinity, something finite, something smaller than 107. Okay, so these things right here, the S1, S2, S3, and S7, they are called the partial sums. The sum that I'm actually interested in goes forever. These are partial sums because they are only part of the forever sum that I care about. And as a list of partial sums, going back to our calculator, it is a list of numbers, right? And what was our word the other day for a list of numbers? Series is our new word for today. Sequence was our list of numbers, right? So that is a list of numbers, and we defined what it means for a list of numbers, a sequence, to converge. Just means it has to approach a single finite number. And it appears that's exactly what's happening here. And so the way that we define this tricky, hey, what does it mean to add a bunch of numbers forever, is to convert that tricky sum problem into a sequence problem, a list of numbers that you create by looking at the partial sums. The first term in the sequence is S1. The next term, S1 plus S2, just add the first two things. It's S2 down there where we added two things, blue and green. And then you add the first 3 terms and you add the first 4 terms, and that is a list of numbers. And if the sequence of partial sums converges to some finite number, then we say that the series also converges to that finite number. Okay. Number 6, the caffeine problem is an example of a geometric series, which is of the form a plus ax squared plus ax cubed plus ... In our example, how much was a? 100. How much was x? It's 0.06, right? Isn't this exactly the series that we just talked about? So it's called a geometric series. The defining characteristic is that every term is the same multiple of the previous term. In this case, the multiplier is 0.06. Okay, the first term is a, and the constant multiplier or common ratio of successive terms is x. The reason we call it the common ratio is that, for example, if you take one term and divide by the previous term, what do you get in this case? Isn't that 0.06, which is the ratio? Right, you can create it by dividing. Okay, the geometric series can be finite, meaning it stops at some point, or it can be infinite. We'll do those on the next page. Okay, in this case, the sum, when there's finitely many of those terms, can be found using this particular formula. S sub n, n is the number of terms, is equal to a, that's the first term, times 1 minus x to the n. X is still that magic common ratio, divided by 1 minus x. And there's this little tricky thing here. It says the exponent is the number of terms. And the fact is I have trouble memorizing that formula, so I derive it anytime I need it. How about we use the formula before we figure out where it came from. Let's do the one example from above. S7 equals, it was 100 plus 0.06 times 100 plus 0.06 squared times 100 plus, what was the very last power for our coffee? It was 6, wasn't it? 6. It wasn't 7 up there. It was 6. Because the caffeine you drank on the first day had 6 full days to disappear. Okay, so we got this thing on the calculator, but we had to hit the enter key like 6 or 7 times. And there's even an easier way than that. So here's the trick to do this calculation. I'm going to multiply both sides of this equation right here by the magic common ratio, which is 0.06. So on the left-hand side, 0.06 times S7. That's just writing out 0.06 times the left-hand side. I'm going to multiply everything on the right-hand side by 0.06. So this first term becomes 0.06 times 100. That's that guy. Plus, what's the next one become? Multiplying everything by 0.06. 0.06 squared times 100. Plus, plus. I'm going to do the second to last one, and then I'm going to do the last one. What does the second to last one become? Yeah. Because the second to last one had a 5th power, and now we're multiplying by 0.06. So now it becomes the 6th power plus, and then what does the last one become? 0.06 to the 7th times 100. So far, so good? Okay, and then we are going to subtract these two equations. Let's do top one minus bottom one. The goal is to try to figure out what S sub 7 is without typing all that purple stuff in. So when we subtract, the left-hand side is just bookkeeping. You just write it. S sub 7 minus 0.06 S sub 7. Nothing to do there. On the right-hand side is where the magic happens. When we subtract top minus bottom, this first term 100 has no partner. It doesn't cancel with anything. So I'm going to write that. 100 minus, and it's got nothing to cancel with. But the next term, 0.06 times 100 in purple, when I subtract, cancels with this first term in the second line, right? And then the 0.06 squared times 100 in purple has a partner that it cancels with. And 0.06 to the 6th, last purple term, has a partner. So is that it? This last term in black had no partner from up above, right? And we were doing purple minus black, so this one is going to get subtracted. Minus 0.06 to the 7 times 100. See it? So everybody cancels except for the first term in one and the last term in the other. And the goal was to find S sub 7, the thing in purple. I'm just going to solve, this is like a basic algebra equation. I'm going to solve for S sub 7. You could combine here and you get 0.94 times S sub 7. I'm not going to write it that way. I'm just going to factor out S sub 7. What's left? 1 minus 0.06 equals, on the right-hand side, I'm going to factor out 100. 100 times 7. Okay, so that's just factoring both sides independently. And then again, the goal was to solve for S sub 7, so here we go. 101 minus 0.06 to the 7th divided by 1 minus 0.06. Okay, so first I want to convince you that the formula we wrote up there, which is sort of pulled out of a hat, it worked, right? A was 100, that's the first term. 1 minus 0.06, that's the x. To the 7, that's the tricky part for me, because it was a 6th power, but it's 7 here. It's the number of terms. That's how I remember it. 7 terms up there in purple, divided by 1 minus x, okay? And it seems like, well, you know, like it was easy enough to type that thing on the calculator before. Well, let's first make sure that we get the right answer. So, okay, so we'll try this again, 100, and then it said multiply by 0.06 and add 100. So this is day 2, 3, 4, 5, 6, and 7. There's the answer. All right. I'm going to compare that to typing this thing over here in yellow. 100 times 1 minus 0.06 raised to the 7 divided by 1 minus 0.06. Do that right? 6. Okay, I think we're good. How's it look? Same thing. Okay. This where I repeatedly hit enter, was that an explicit way of calculating or a recursive way of calculating? That was recursive because it relied on the previous answer to get the next answer. This magic formula right here, was that explicit or recursive? That's explicit. And it seems like in this case, whatever, one or the other, it took about the same amount of time for me to do both times. But if I wanted the 100th term in this list, well, that would be pretty darn annoying to do the recursive way. But the 100th one here, just change that 7 to 100 and you're done, right? Easy peasy.
How many terms would you need to go out if I went to day 7?
Yeah.
How many terms or how many days would you need to go to derive that formula? Second, third day.
To derive the formula? Here?
Yeah, that sub in the formula we just.
I think in theory you could just do one term and just multiply it and then subtract. Yeah. Okay. Good. All right, next page. All right, number 8. Chessboard is an 8 by 8 square. 1 penny is placed on the first square, 2 pennies are placed on the second square, 4 pennies on the third, 8 pennies on the fourth, and so on, right? Doubling every time. 1, 2, 4, 8. Next one will be 16. So the question is, what is the total value of all of the money on the chessboard? So in this case, we are doing, I'm just going to do this in pennies here. So we got 1 penny plus 2 pennies plus, okay, I don't want to write 4 and then 8 and then 16. I want to write a formula here. So 4 is really 2 squared, right? And 8 is really 2 cubed. And in fact, while I'm doing this, 1 is really 2 to the 0. Okay, and then I'll just, okay, now I've really got my pattern laid out nicely here. Plus dot, dot, dot. Just got to figure out what we're putting at the very top. Yeah, let's see. So it's an 8 by 8 square, so that makes 64 squares. So what is the power up here? 63 is right. If you're not sure, this was the first square, this was the second square, this was the third and the fourth square. And we were just looking for this relationship, the square number and the power. And it sure looks like the power is 1 less than the square number. So if I'm doing the 64th square, then yep, 63, 1 less. Had better be the thing to put up there. Okay. That right there is called a geometric series because every term is the same multiple of the previous term. What's the common multiplier in this case? It's 2. This is geometric with x is our name for the common multiplier. X is 2 every time you double to get to the next term. And our letter for the very first term is always going to be A. How much is A? A is 1. A is the very first term, 2 to the 0, which is 1. And N is the number of terms, 64. It's really tempting to grab that 63. It is not. It is the number of terms, which is what I just did there. See how tempting it is? 64. Okay, so we've got a magic formula. Just grab your magic formula. It's on the previous page, right? We're looking for the sum of all of those guys right up there. S sub 64 equals. Okay, what's the first thing? Yeah, we got the A is 1 times 1 minus, what goes here? 2 to the 64 divided by 1 minus 2, that's it. What do you have on the calculator? Okay, so that's how many pennies are on the chessboard. So in terms of dollars, this becomes what power? 17, right? Okay, let's see. So yeah, so right, so 10 to the 6th is million, 10 to the 9th is billion, 10 to the 12th is trillion, 10 to the 15th is quadrillion, and then 10 to the 18th is quintillion, right? So that is like 18 quintillion dollars sitting on that chessboard. Than will ever exist in the world.
There's like $60 trillion.
I'm generalizing. I am. This is still more. Okay. All right. I think that's good there. Let's move on to the next example here. Geometric series can also be infinite, meaning it goes forever. So capital S there. I didn't point this out before. We've been using capital S's today to represent the series, whereas yesterday or Friday we did lowercase s for a sequence. It's a small difference. Okay, so S sub infinity doesn't mean you're going to get infinity when you add them. It means we are doing infinitely many terms. So it just goes forever. It turns out that in this case, it's actually even easier. The magic formula is even simpler than the one that we talked about before, because if you remember the calculation that we did here, when we do the subtracting, so the 100 had no partner to cancel, right? And then everybody else had a partner except for which one? The last black one over there, right? But if we are doing this thing forever, so purple goes forever and black goes forever, there is no last black one, and every single one has a partner except for the very first one. So the last one, that 0.06 to the 7 times 100, this one right here, which ended up right here and also ended up right here, does not exist. So this formula does not have that. And 1 minus nothing is just 1, so that doesn't contribute anything either. So it becomes just 100 over 1 minus 0.06. In this case, it becomes a over 1 minus x. It's just that. Let's write that on the next page. S infinity equals a over 1 minus x. Okay, now you got to be careful. We're going to use that formula, but you got to be careful about when you use it. This thing in blue here, our chess example, the magic multiplier, the common ratio here was 2. If you did this adding the blue things here forever, what would you get? Infinity, right? Clearly you get infinity if you add that thing forever. So the answer should be infinity. If you just blindly try to use this a over 1 minus x formula in that case up there, a is 2. So don't write this because it's going to be ridiculous. A is 2. No, a is not 2. A is the first term. Was 1 divided by 1 minus the common ratio 2. But clearly the answer should be infinity. Definitely not -1. There wasn't anything negative in that series at all. So for sure the answer is not -1. So you have to make sure that you only use that purple formula when the series converges. The thing going to infinity means the series diverges. It's the definition. And so what kinds of things will allow us to have a series that converges? Well, if we take a look at our coffee example, what was the magic multiplier? 0.06, which made it so that the terms are getting small, 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 tiny, 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 as opposed to the chessboard where the terms are getting bigger and bigger and bigger. That's the difference between converging or diverging for geometry. If the terms get smaller, 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 closer to 0, it's going to converge, and you can use the a over 1 minus x. So what kind of multiplier, what's the cutoff for the multipliers that converge and diverge? 1, isn't it, right? If you double, that's on the wrong side of 1. If you multiply by 0.06, that's on the correct side of 1. There's got to be another number on the other side. Like 1 is one of the cutoffs. What about smaller than 1? What's the 0, right? Like definitely anything between 0 and 1 like this 0.06 is going to work. Can I go on the other side of 0, or is that just automatic diverge? What if it were negative 0.06? It would still converge. Negative 0.06 is going to make these numbers closer to 0. Pluses and minuses and pluses and minuses. So the other side is -1. Anything on the wrong side of -1 diverges. Anything on the wrong side of +1 diverges. But we've got this magic window in between -1 and 1 where we converge. Yeah, if your magic multiplier was 1, you would just keep adding the same number over and over again, which will diverge. So yeah, so here's our fancy infinite formula, and Nick points out it is a strict inequality, only between -1 and 1 strictly. Anything on the wrong side of -1 or the wrong side of +1, and the infinite geometric series will diverge. Okay? That's for x. Yeah. Okay. So let's just do our last example here with the caffeine. S infinity equals, what was the A for the caffeine, first term? 100 over 1 minus x, 0.06. 100 over 0.94. Okay, this is what we got after 7 days. If I, let's go back, second enter. Okay, so I'm just gonna do this guy again until we run out of digits. Okay, there we go. All right, so that's day 2, 3, 4, 5, 6, 7, 8. All right, so after 8 days, it's exactly the same set of digits. What am I typing in? 100 over 0.94. Bam. Yeah. And don't be deceived. This thing changes. Like this guy right up here is not the right answer. This one down here, which looks exactly the same, is the right answer. It only looks exactly the same, but it's not exactly the same, right? So more common than typing in an approximation from the calculator is to convert this guy into a fraction. So let's see if it does anything. There we go. 5,000 over 47. That is the limiting value of the caffeine in your system. Any questions on that? Okay, so the activities are there. Let's see how far you can get. I will walk around.